Yeah, so today we at this moment we just need to be straight to the point without much explanation about so many concepts. So one of my students asked me a question. He asked me that question in a way that I now realize that many people are confused about these things. He asked, why is it that we have different colors of light in the most of the LEDs we use in the lab for electronic components? Why is it that this one is blue, this is red, this is yellow, and so on? Different color indicators. So I now say, wow, so this means that many people, even after A level or O level, may not have even grasped the main reason behind that, the physics behind the technology. So I thought it was to come and explain clearly what actually brings about the color variations. So now, in nutshell, what we know from our previous knowledge in elementary physics, we already know that we have different kind of engineering materials. And then, particularly for LEDs, we say they are made up of semiconductors. Okay, and when we say semiconductors, what we mean is that they are conductors and they are not automatically insulator, they are not automatically a conductor. So semi means intermediate, they are in between. So and what does that supposed to tell you? What it's supposed to tell you is that they are semi means when you heat up in terms of firing the temperature, if you elevate the temperature to a bit, it will now move from a valence band to a conduction band, and then conduction continues properly. So this is not just mere verbal discussion. It has a lot of mysteries behind, and that mystery is what the physics is all about, and that is where the concept of technology plays around. Because the type of material you do in the course of growing your crystal, your semiconductor crystal, can actually affect the color of whatever thing you are designing. So now let us go to the board. Looking from the perspective of an engineer, we already know that we are taking this as a profile, a material profile, semiconductor material profile that have these two regions. These two regions, we are taking this side as a region 1, which is the valence band. The valence band, when the atoms are properly arranged in the crystal, when they are properly arranged, the temperature is still normal. And then this side is the conduction band. So this region now, there are two regions. You see that there's a gap between the two. So when we are told that by the time we heat up this region, this material, the atoms here can excite and then move to the other side, and then the conduction kicks up. So there's a little magic that happens within this gap. So that this small difference here is where the mathematics happens, and that is where the photon is being emitted. That is where the physics is played in. So when you hit these things, there's an energy that is going to be emitted. That energy is going to be emitted in form of a photon, and that photon is going to have this kind of arrangement, Hc all over divided by the lambda. And what we know when these things light behave as a have a dual property, can behave as a particle, can behave as a light. So this, the Broglie and all of them plants, they have already coined that this energy is in this equation 1. So this equation 1 here, Planck's constant is 6.626 times 10 raised to the power minus 34 joule per second. Then this is speed of light 3.0 times 10 raised to the power minus to power 8 meter per second. And then this is the wavelength of in nanometers, the wavelength of whatever whatever particle that is exchanged here, the wavelength of that wave is going to be either in nanometer or in other units of meters. So this is the genesis. Okay, so what actually happens is that when you begin to dope the material, when you are trying to grow your crystal, the semiconductor crystal, of course, has to be this way, PN junction. So the PN junction at that region has to have a hole and then it has electrons. So during the time of that recombination, energy is emitted. That energy which is emitted is in form of energy band gap. And this energy, no matter how small it is, can affect the color of the diode. That's what I'm trying to explain. That the energy is as a result of the color is as a result of the energy difference. So if the energy goes high, there's a color spectrum that we are going to enlist for you. So you have the LEDS, okay, the LEDS. This is the color spectrum. Let me write it properly here. LEDS representing the colors that is possible for these LEDs. So these colors that are possible, this is red, this is orange, yellow, green, blue, indigo, violet. Okay, so if this one has the if in terms of frequency, if you are going to say have the highest frequency, of course, the conduction, the wavelength region will be around 620. So this is 620 nanometer for red light. And then by the time you play with this, of course, you know that if you are converting the energy band gap in electron volt, you are going to have something like this. If you are converting it, you have 1240 all over your wavelength in nanometer. So if you are taking 620, which is for the red light, you do this conversion now, you have close to 2 point something electron volt for red for red lights. Okay, and so on and so on and so on. So it is not the encapsulation, what you use to cover the filament that is giving it the color, but the energy gap that is being emitted by the recombination of the electrons and holes within the semiconductor material you've used to dope the material during the time you are growing your crystal. Thank you very much. Thank you so much.